Hello everyone and morning. Today we're gonna talk about representation learning and see how it works and what's the representation learning. I will try to cover uh, the area and give you an idea what's the concept and why we are doing it. And I will cover literature's ideas in this field. Let's go and start by definition. Uh, as you might know, the word is a complex structure of the facts. Like objects, they are also interacting with each other. As an agent, machine, or your AI system, uh, you should understand these interactions and objects. Um, Maybe because the sensors are limited or the word is more complex than what you can think. So we're trying to understand just the general concepts in one integrated space, I would say. Or if I'm gonna say it in programming languages, really small numbers as much as we can, a smaller space. So let's say we have like some pictures as our input data. We're gonna understand what's the main concept of this image in the word. And as an agent, when we are learning that concept here, is more clear than this complex image. And when you will understand how the image is in the real world, then you can come back and answer your question that you had before. For example, you wanted to know what's the objects in this image. This process that I just briefly talked about is the representation learning, and this one in the new space is the representation of the input. And from data, we're coming with something which is more meaningful for the input network or the machine. So if I will go through it by the pre-deep learning models, let's say we had some input images, and what we were doing was the feature extraction on top of these images. Let's say we were finding what's the gradients on the image, and then after that we had some handcrafted features like where the body is, where the hand is, and then let's say these are the small objects of the body, and then we were trying to understand how they're interacting together. Let's say the head should be on top of the hands and stuff. And then at the end, if we could find some interaction here, we were saying this is the human based on the classifier like SVM. I will just like mention all the references here in the slides, and then I will share them also with you so you can learn more if you want to know how this model actually works. But right now in deep learning, we're not actually doing these things handcrafted. Let's say we had an input image. There's a magic box here. We're trying to understand these features by itself. So we'll feed this one into the network, and then we'll get the output which says this is human, or where the human or the person is in the scene. Right? So supervised representation learning is look like that you are putting an input, let's say image, and there is a feature extractor here, and then there is a task like classifier. Okay, this is the supervised learning, so you have the classifier. Is it cat or is it dog, or what is inside of this image, let's say. And if you could train these kind of networks which can classify input image, then you will come up with one feature extractor as well. If you're just like looking at this schema maybe more wisely. So if we'll drop this one and using the feature extractor here, we can change the classifier to something else. Let's say we can use the same feature extractor for the object detection, for semantic segmentation, for visual question answering, for anything else. Because this is the feature extractor that can find the objects, maybe also the relations and the interaction. Then we just need some classifier on top of them to understand what is this objects and interaction means in a case of concepts. But the thing is, when you wanted to have the classifier here, it means you need the label as well, right? It's working by the labels. So this is supervised, right? When you need the label here, so it means your training data should has the label. And finding the label or making some data set with the label is expensive. Maybe if you want to make one, would be expensive for you, right? Or even if you have lots of funding, it's time consuming. You should go and like label hundreds of millions of data, right? Or at the end you will come up with error because humans are annotating this data. So what we are aiming to do is just finding one better solution to just skip these parts and using this feature extractor or training this feature extractor without the labels, right? So why we need the unsupervised learning? I just said like if you want to have the label, most of the time is not possible. But if I'm gonna be precise on when you are looking at the nature data or human intelligence, when you have a baby, a kids, or even the animals has some idea about gravity without telling them or without teaching them what the gravity is. Okay, nature working without most of the time labels. Okay, you're not training people by telling them this is gravity. Maybe they're just exploring the world. Or if I would say another reason is right now there are millions of posts every day in social medias, or there are lots of blog posts, news out. We're creating content on the internet, but there are not labels on them. So if we want to use that data, so we should go for unsupervised, because the data doesn't have most of the time label on the internet. And like, I mean, crawling when you are crawling it without any inspiration. And the last one, and not least, is answering the new questions. The classifier was just telling us this is a cat or dog, but we need to know more. Okay, how's the position of that cat is, like what's the, where is it? The lots of other questions. So the classifier itself engineered for the specific type of questions. Cool. So the notation is look like this. I'm not going through formulas today, but just for understanding, if you are going supervised, it means you have some labels, which we are using it here. We are showing it by the Y. And given your data, you are understanding what's the probability of that labels given that inputs. But with the unsupervised, we don't have any labels, so we'll just understand how's the data look like out of the world. So it's very good, right? So it's like we're just skipping one parameter as an input, and less parameters is better, maybe for engineering. There is something else called self-supervised representation learning. To just get familiar with, we are actually using some pseudo tasks. Let's say we are generating some fake classifiers which can make some fake labels or pseudo labels. And in this self-supervised representation learning that you might see later on in my presentation, you're not using the labels. Okay, these labels are actually generated, and I will show you how we are generating these labels. But this is a trick that the input has some labels, but that labels are not actually the real world labels by the human annotated label. I mean, and in this case, we can do it low cost because it's a machine that generates the data, or I mean the labels, and it's more scalable. You can just have an input of millions of data and do it as well, and it's flexible. You can change it with the different data. And why we are doing it, I actually brought you some interesting results here. This one is from NLP, and this one is from computer vision area. And it actually shows the function of ImageNet performance task and classification, which you have the input image and you will say what's the class of it is, and the percentage of labeled data and the model which was trained on. So the red one is the model that had the supervision on. So you had all the labels during the training. And the blue one is the one without the labels. And when you were decreasing the number of labeled data for the red one, when you had one labeled data, one class of labeled data, you were even just getting like 45%. But if you were doing it by some sort of unsupervised classification, which was trained generally, and then it was just using for a specific label, we were getting like 75, which is a really huge difference. So people shown that like you can have the model with the unsupervised training, and it could work like in ImageNet very good, or even in NLP, they showed that, and you can see it right now that we're merging the data sets, and we're using the unsupervised type of the input for training the network in task 1. Let's say it's question answering. You will ask question from the network, and then we will use that one in another task like language modeling. So when they were integrating the data sets together and we're training the model again, you will see that a specific model without the pre-training can work very well when you have just like having some bunch of unrelated data, which they are not unrelated, right? So there are languages still. And you can find a feature of the language in, right? How you can make the sentences regardless of the task itself. Okay, let's dive in, and I will show you how this one exactly works. So we got some elements I will show you here, and I will use these elements later. So if we have the input X, which we are showing it here by some rectangle, we are putting it in some neural network. We call it representation network. You can see it as encoder inference network with different names, but all of them are getting the input X and coming up with something as a representation that we are showing it with R, and this representation is actually the thing that we are searching for. Let's say if you have an input X, this representation can have different size. It could be a smaller or larger. Here we wanted to have a smaller type of representation, just a compact representation as I mentioned in the example. Or in some cases you can have larger. How is the structure of this representation is? For example, the representation could be just a number that when you are looking at them, it's not interpretable, or the output could be strings that you can just see and understand what does it mean. Or it can have some type like continuous or discrete or it could be fixed or variable or disentangled that we'll see in the next model. And this encoder networks has different types: multi-layer perception, convolutional transformer, recurrent neural network. Whatever you're calling it is just like get the inputs and make you the representation. There is something else that we are call it generator or decoder or generation networks, which get the representation R and feeding it to the generator network will get the output X prime. So this generation network actually mapping the representation to the real world or output X prime. And the network, again, could be multi-layer perceptron, it could be deconvolutional transformer or recurrent neural network. And if you put these two together here, you'll come up with the autoencoders that you might have heard about. We changed the field during the years. So the autoencoder is just the one model, I would say, which can get the input and you'll get the output after representing it to this space or to this representation. Cool. And what the autoencoder can do, we will see here. So if you have some X, this one is X, I will correct it later, to the representation network, and then getting one representation and doing it by generation, you can use it for density estimation, for example. Let's look at this model, which is the first one, like one of the first models in 2006, which was getting the human face and was generating another one with some convolutions like 2000, 1500, and there is a code layer in between with only 30 numbers, and we call it representation. So you can do it density estimation, like how's the input is, or you can just use it for dimensionality reduction. So how it works is like you have this input, you're gonna compress it, right? So you just like put it inside the model, and you will get the compressed numbers, less numbers. And then if you're gonna decompress it, you will just like put it in the generation network. Or you can generate images. You can just like put an input image and you will get another image. Or you can denoise the input image, or we can use it for representation learning, which means if the model is trained enough and you will put one image in, you will get the best representation, best latent space, best numbers here that shows the most important part of the input image. So these are the objects inside the image, and we skipped all the other details which is not related to the face. Face could be just these 30 numbers instead of these input matrix. Is it clear? How many of you are following me? Just raise your hand. Okay, cool. Okay, let's go a step further. The autoencoder also can show you all the new variable space, or how the new variable space works. Let's say here we have the code layer as an input. So we'll skip this encoder and we'll just like have the decoder here. So you can just input the random numbers here, and you will see how the output is. So if we will change it, like let's say there is an numbers here, one by one we'll changing the input numbers, and we'll get the different outputs. So, and we can see all the outputs, all the possible faces, all the possible input numbers in the word. And this model actually was showing all the numbers, number word. If that would be some magic box which can shows all the face, then you can see the people face, like all the faces, all possible faces in the word, right? Because the model can generate them for you by just like changing the representation. Good. So if I would go one step further, there is something called discriminator or contrastive learning or contrastive networks, which can tell you if the input image is in the proper definition or if it's real or fake. Let's say if you have an input face, it can tell you if the face is in that space or not. Then if it would be in that space, then it's a real face. Okay? If it's not, then it can tell you it's not. So regardless of the labels, you will put different inputs and it can tell you which input is fake or real. And if I will put these two things together, I will come up with a GAN, or general adversarial networks that you might heard about, which is the hype, right? And what it does is just making the representation, and then you will just like use the representation for understanding the fake or input image. Fake or real input image, right? And it actually works that you might see it can generate, and what's the idea in between is the, right now here, after training, if you will do it correctly, then there is a generator here which is getting that space and can generate you the fake images, okay? Because this network can understand fake or real, right? So you can use it for distinguishing the fake or real image together. How? You will just like put one random number here, you will get an output. Then you will put the output inside this discriminator. The discriminator tells you this is the fake. And you will change these networks till the time that the generator can make a fake input image which the discriminator cannot understand this is the fake, which means the fake generated image is actually in the space, right? And you will come up with this interesting output, which these are the face, but these are not the real humans. These are just generated. Or these animals and the burger here is not actually a real burger. Okay, this one is generated. Or the scene over here. You might see some noises here if you look at the images precisely, but they are really incredible, right? So the generator is actually work. And if you're looking at this GAN over here, you cannot actually make or learn the representation given X. Okay, because the representation is an input. But if you would be like a bit wise, you can just a bit change this model and you'll come up with the new model like Python, which has one representation network generator and discriminator. And what the discriminator is actually do right now is working with the input and also the representation, and it can tell you if the representation related to the input or not, or the input is the good if the representation is a good representation of the input, or the input is the representation, or they are not related together. Then you have another input here that you can do the same. And you can also understand the x given r and r given x. And you can generate the data as well. Good. The Bayesian is actually works. And even more interesting. So for example, look at this image. This one is the input, and we ask the Bayesian to make another input look like this input, because we have the input here, and then we ask the generator to make it. So we put this input inside the representation network. We got the R, we put both of them to the discriminator, and then we had the generator there. So we put this image and ask the network to make another image look like this image. And what it did is interesting, because it made another image here, which has the main part of the input image. Here is a scene with some farm, and you can see the farm and the scene. But this one is the auto is like a tractor. But here you will see something else. But it's actually the same idea, same concept of the scene is there. Or this one is also interesting. This is a pizza as an input, and you got another pizza. It's rounded in the same view, but maybe this is like vegetarian one. This is another something else, right? Generated one. But both of them has the same concept, right? This one is generated, but with the same type of concept. And GANs also can use for different things. These are interesting things which I'm gonna just share with you. That is not just for generation. And most of the supervised tasks can also conduct with the same idea. Let's say we have this one. This is the grayscale image. And you want to colorize this image. Okay. However, doing it in the supervised techniques, we had like the gray image and the colored image. And the colored image were the labels, right? Then here we will ask the network to make the label as a color of each pixel as an output. So the output is the color per each pixel. And then we can just like make the picture color. Or you can do it somehow different. You can have an input image, and the representation network can tell you what's the rotation of this input image is. And how the representation network is actually really simple idea. So it was trying on the different rotated image. And what was the objective was that try to predict the how much this image is rotated comparing to the zero rotation, 90 degree, 180, 250. And then at the end, the representer or the network could tell you if you have an input image, maybe it is rotated 90 degrees. Okay? Good. And these are actually we are calling them self-supervised learning because you already have this input. So these are kind of generated, right? We just generated these ones as a label. And there is a different type of applications which you can just go and see. It can just paint you the unpainted part of the input image. It can drive you to home or can do different type of things. It's not actually limited to the one application. I'm using the computer vision examples here, but most of them also applies in NLP. It can use for automation in different areas. So you can just change the input and the output based on your problem. So any quick question till here? Just quick one. Mm-hmm. 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 So we actually haven't had that kind of labels, so we were just learning them, right? So it wasn't actually an input label. So I will just go through and we'll come back by the questions, right? If you have any. Yeah, if you can just change the application, right? If you have an application that can understand this is the fake, so maybe it can also tell you how much it changed if you just precisely change the outputs, right? If you can just modify and define your problem correctly. There is another part of the presentation which I really want to cover as well, based on the time, which is contrastive learning. And it's based on different ideas. Let's say we're gonna again classify the input image. The idea is if we have the space of the input images. So let's use this fact which is in this space, maybe these points, these cats are more similar to each other and they are far away from the other classes like the dog. So let's make one model can understand the similarity of the images instead of using the pseudo labels, for example. So in these techniques, we have to be precise which data points are similar and which ones are dissimilar. So we don't have label, right? If we had the labels, like if we were in the supervised representation learning, we had the labels, so we were putting this image inside the network and we were fine-tuning the network based on the label. And if this is a cat in the training, we were just changing all the weights over the network to make the cat as an output. But here we don't have the labels. Right? So the question is how we can find the similar and dissimilar in input data and then train the network. And then after that, the trained network can tell you if they are similar or dissimilar. So what we are doing for dissimilar, if your data set is big enough, if I will go and pick 2, and the data set is really good, is well normalized in the space, most probably that two random data points are not similar. Maybe some of them are, but like generally not. So for this similar, we will just like pick the random selections of the input images. But what about the similars? And for similars, we can do something interesting, like making the artificial input image look like this one, like similar to this one, but not this one. Maybe from different views or multiple views. And how we can do it is also lots of techniques. But let's say I can just like get this input and crop it and resize it in different areas. This one is still the same cat, and most probably they are similar in that domain, right? Or I can just augment this one and crop it, rotate it, just putting some noise in. But it's still the same cat, right? Oh, that's awesome right now, right? So we have these similar and similar ones. Then we'll train the network. And then after training, the network can tell you the class, which doesn't know the class of the cats and dogs, but it actually can tell you which one is. And this is one work which is using the same idea. You have the pairs, the negative pairs, and the similar pairs. These ones are similar. So we have an input. We will make two artificial input image, which they are actually the same, and one random image as an input, let's say. Okay. Then we have the representation network. We will get three representation, and we have some optimization or loss function, right? What's the loss function do here is we will tell the loss function these two should be similar to each other, so they are attracted, so make some weights which can make some similar representation for these two, but this one should not be related to this one, okay? Or this one should not relate to this one. And then we trained all the network. And the last things that I'm gonna tell you as the conclusion, which the field is going on, there are really complex model like this one, which I'm not going through, which is in ICLR 2022 from the Google research, which can generate the output image. This is the input, and this is the reconstructed output, which you will just put this input and will ask the network to generate you some output images, which is not actually look like this one, but from the same class. It's use the transformer, you just like make the similar points transformer, and then there is a pairs. It has some details. But what it does is interesting, because you can just like put a class, like one sample, and it will generate you the samples look like that class. Like you can put the night snake, and these are the generated night snakes from the class, from the network for the input class, or the different classes, which these are the samples from the text. And that was pretty much of it. And you can find the slides here. And I would be happy to answer your questions if you have any. Thanks for attention. Yeah, sure. The microphone.
So you showed us examples of, let's say, contrastive learning on images. Is there a practice to use contrastive learning on tabular data?
On which data?
Tabular.
So personally, haven't worked with that data. Again, I will answer the same question as the previous one. If you could represent them as like the inputs, and you can make the outputs, I don't know like which kind of task you have in that domain. Most of the time, you can use them. It basically relates to the distribution of the input data, the outputs, how big is the spaces. But if I will just answer you generally, it works. But to be honest, I haven't worked personally with that data.